So in my talk today, I will focus on topological superconductivity and Majorana states in atomic scale magnet superconductor hybrid systems. So I would like to bring together the two fields of this conference, magnetism and superconductivity, and I will discuss novel exciting states, Majorana states, in atomically fabricated chains with the use of the scanning tunneling microscope. So first of all, I would like to introduce Majorana states because not all of you might be familiar with this subject. So Majorana was a famous elementary particle physics theorist, and he predicted that there can be fermions being their own antiparticles. And he arrived at this conclusion by considering basically solutions to the Dirac equations different from a solution which was derived by Dirac in 1928. Dirac basically proposed complex solutions to this equation describing particles and antiparticles which are not equivalent. So for instance, describing electrons and positrons. On the other hand, Majorana proposed a few years later a real solution which is able to describe particles being their own antiparticles. And this is, of course, of great excitement. Already in particle physics, of course, for a long time, people have been searching for those particles, and there have been discussions whether neutrinos would be realizations of such Majorana particles. However, as you all know, in the standard model of elementary particle physics, neutrinos and antineutrinos are different particles, and so this discussion is still ongoing in particle physics. However, in solid state physics, we have indeed possibilities to realize Majorana quasi-particles, and this is what I'm going to discuss next. So in condensed matter, as you all know, we have electrons and holes being the equivalent of particles and antiparticles, and especially when considering superconductors, we have a very nice electron-hole symmetry, which plays a crucial role in this field. So as you all know, if you consider the energy spectrum here of a superconductor with the superconducting energy gap here, then of course under special conditions, for instance, if we have magnetic impurities interacting with such a superconductor, we might have discrete states within the gap of the superconductor. And these electron and hole-like states, which are induced, are symmetric with respect to zero energy. So if we want to have the electron and hole-like states becoming equivalent, the only way to get this is, of course, if we finally end up with a zero energy state, so-called zero energy mode, and under special circumstances, these have all the properties of these predicted Majorana states. However, the problem is that in an ordinary S-wave superconductor, there is no bound state right at zero energy. So one might go towards P-wave superconductors. However, these are either complex materials or it is also very difficult to actually prove experimentally this P-wave nature. On the other hand, it has been proposed that exactly this situation might be realized in hybrid systems of superconductors with, for instance, semiconductor nanowires or magnetic nanowires. And so, first of all, the focus of this research was on hybrid systems of semiconductor nanowires proximity coupled to elementary superconductors like aluminum and other kind of elementary superconductors. And in 2012, two groups reported on the observation of such zero energy modes in such semiconductor nanowires like indium antimonide or indium arsenide, proximity coupled to aluminum or other kind of superconductors. And they did transport experiments as a function of magnetic field from 0 Tesla to about half a Tesla or so. And then they have seen a peak at zero energy here, which shows some characteristics of these Majorana states. However, a few years later, it was also seen that especially disorder at the semiconductor-superconductor interface can actually also give rise to such zero energy states. And another problem has been that the transport experiments were not able to spatially resolve the Majorana state wave function. So this is why we focus here in this talk especially on scanning probe techniques, which can access basically the spatial nature of these states. So here I would like now to introduce the second platform, and especially this is the platform which I'm going to focus in this talk, especially because this is a conference on magnetism and superconductivity. And indeed, if we create hybrid systems of a magnetic atom chain interacting with an elementary or other kind of S-wave superconductor, then we can get not only the trivial bound states induced by the magnetic impurities, the so-called Shiba states or Shiba Rusinov states, but under special conditions, we also can get at the end of those chains the emergence of so-called Majorana bound states. This has been theoretically predicted by a number of groups, and this is, of course, extremely exciting because here we can make use of tools like scanning tunneling spectroscopy to access these Majorana states. Now, let me discuss in more detail the physics behind these Majorana states. So, in theory, first was proposed that one should make use of atomic spin chains with a helical magnetic state interacting with a superconductor. What happens then is that the Shiba states of the individual magnetic impurities will then hybridize and form a one-dimensional Shiba band. And then if you bring together high spin orbit coupling and the magnetism, then you split basically these bands in momentum space as well as in energy. And if you also have a fourth ingredient, namely superconductivity by proximity coupling, then you can induce a topological superconducting phase with a characteristic band structure as indicated here. And at the ends, basically, of those systems, boundary states are predicted to occur then, because at the ends of these chains here, these bands will touch each other and induce zero energy modes here. And this, of course, should show up in the local density of states here by a very sharp peak right at zero energy. And on the other hand, these states should be highly localized at the ends of this chain here. This has been predicted, and of course, lots of experimental groups were looking for these signatures. However, this is not an easy task because you have to have tools which allow for the fabrication of very well-defined atomic spin chains. You have to control the magnetic state of the chain, and you have to have very high spectral resolution to probe these zero energy modes, and you have to have a high spatial resolution to really see the localization of these zero energy modes at the ends of those chains. So I'm only aware of one experimental tool which can bring together all these necessary ingredients, and this is the spin-polarized or spin-resolved version of the scanning tunneling microscope, which we have pioneered about 30 years back in time. This basically correlates then the atomic level structure, the local electronic structure, and the spin structure at ultimate spatial time and energy resolution. And the basic idea is that you functionalize a probe tip in STM by a magnetic cluster or magnetic coating or even a single magnetic atom with a very well-defined spin state. And then you look for the spin-resolved electron tunneling between this magnetic tip and your magnetic substrate. And the spin-polarized current then depends on the cosine of the angle between the magnetic moment on the sample and on the tip. That means nothing else than looking at the projection of the magnetic moment of your sample onto the spin quantization axis, which is given by the orientation of the probe tip. And the spin polarization of the sample and tip basically determine the magnitude of this magnetic contrast. So if you want to read more about this, this is one of the review articles I have written for this field. So first attempts to observe Majorana states in these magnet superconductor hybrid systems have been reported by the Princeton group of Ali Yazdani. So already in 2014, they reported about the zero energy modes really localized at the ends of self-assembled iron chains, here in this case on a lead 110 substrate. And 2 years later, actually the same group published another paper on exactly the same kind of platform, but in this case, they reported on a double eye feature, which actually is located a little bit away from the end of the chain. And that was, of course, very puzzling. There were two contradictory observations, and theorists tried to model this by a more complex structure of the chain, a crystalline iron chain, which is not monatomic, but has a more complex structure. But if one looks at the experimental data published in this reference here, conducts measured along the chain here shows irregular structure here. It's not periodic as it should be for a crystalline wire. This means, of course, that there's a disordered wire here. It's an amorphous wire because of intermixing between iron and lead. And this means, of course, that you cannot compare one-to-one between experiment and theory. And the major concern was, what is the role of the disorder? Very similar as for the semiconductor nanowire system. The disorder can also induce low energy states, and this problem could not be solved. So in my talk, I will get rid of this problem of intermixing between iron and lead in this self-assembly technique by making use of another technique, namely single atom manipulation, which was pioneered in the early 90s by Don Eigler. And it works like this, that you approach your scanning tunneling microscope tip towards the magnetic atoms on surfaces, you drag these atoms on the surface and leave it at a new position, and then you withdraw your tip. And you can do this one after the other with many atoms to create chains. Now, about 11 years back in time, we reported for the very first time of a combination of the single atom manipulation technique with spin sensitivity. So we could do this since then with magnetic probe tips and magnetic atoms without changing the spin state of tip and atoms. This is a quite challenging task. Now, let me introduce the experimental system I would like to focus on first. And these are iron atoms and chains on a rhenium 0001 substrate. Rhenium is an elemental superconductor with a TC on the order of 1.3, 1.4 Kelvin. And here I first introduce individual iron atoms, which are deposited from the gas phase onto a clean rhenium 0001 substrate. And first of all, we can notice that we have iron atoms here on inequivalent adsorption sites, as revealed by atomic resolution scanning tunneling microscopy. That means that we have either HCP or FCC adsorption sites. And this difference already shows up in the apparent topographic height, which is different in the STM contours if we measure above the iron atom on the HCP side here in red, and on the FCC side given here in blue. Now, this is, of course, not much of importance for the physics, but what is important is that the Shiba states induced by these magnetic impurities depend drastically on the particular adsorption site. So here is data where we plot now the differential tunneling conductance, which is a measure of the local density of states as a function of sample bias, meaning as a function of energy. In black, you can see the spectrum measured on the bare rhenium substrate. And then in red and in blue, you see the spectrum measured above the iron atom on the HCP or on the FCC side. If we subtract the rhenium background spectrum, then we end up with these spectra here. And here you see very nicely the two component structure here of the Shiba states for the iron atom here on the FCC adsorption side. For the iron atom on the HCP side, you see basically a single peak only if we use a non-magnetic, metallic, non-superconducting platinum iridium tip. So it appears as it would be some kind of zero energy mode here at these iron atoms on HCP side, but this is not the case. It's not a single peak, and you can see this if you replace the normal metal tip by a superconducting tip, namely a niobium tip. Then you have actually a vacuum superconducting tunnel junction, and you improve the spectral resolution drastically. So you see the coherence peak then, of course, at the sum of the two superconducting energy gaps for the niobium and rhenium, and you have much higher spectral resolution. And with that, we can really solve the two components of the Shiba state of the individual iron atom on the HCP adsorption side. But the difference, as you can see here, is only 20 microelectron volts. So you have to have extremely high energy resolution in order to resolve this. For the iron atom, on the FCC adsorption side, you can see here much better resolved two-component structure now. Basically, the two Shiba state components are now separated by about 100 microeV. So what we learned here is that Shiba states do not only depend on the particular magnetic atom and the superconductor we are choosing, but they can even depend on the particular adsorption site. That's amazing. And that means you really have to control every detail in your experiment, even the individual adsorption sites, when doing these kind of experiments. So what we do now next is we go from a single atom towards the construction of chains atom by atom with the help of the single atom manipulation technique. And then we can really look at the physics of these hybrid systems consisting of monatomic spin chains interacting with a superconductor. So here you see basically a sequence now of atom manipulations here. We start with single iron atoms. We make sure by local spectroscopy that these are indeed all individual iron atoms, and we create here, in this case, a chain of 40 iron atoms. We make sure that all these iron atoms reside on HCP adsorption sites. We basically create a chain with close packed spacing between the atoms, and so the periodicity of the iron atoms is basically given by the periodicity of the rhenium 0001 substrate, which is 2.74 angstroms. So we have everything under control experimentally, and so later on, as you will see, we will be able to really compare then the theory in a one-to-one fashion. There's no ambiguity here left. We control everything atom by atom. The next step is, of course, that we also have to get information about the magnetic ground state of this system. So therefore, we then do experiments not only with a non-magnetic tip. Here you see again this 40 iron atom chain here and the perspective topographic view. But you see now, if we go towards a spin-polarized tip, a chromium tip in that case, we see in addition now to the topographic image here, an additional modulation here in the constant current traces here with a spin out of plane sensitive tip or with a spin in plane sensitive tip. So there's a clear difference here in the corrugation. We can analyze this quantitatively by making one-dimensional Fourier transforms of all these data sets, and this is shown here. In this Fourier transform, we see then a peak, which is a trivial peak. This peak corresponds to the atomic periodicity of the iron atoms along the chain. And indeed, with all different tips, the non-magnetic, the out-of-plane and in-plane spin-sensitive tips, we see this peak. But then we have two additional peaks here, which are actually seen both with spin out of plane and spin in plane sensitive tips. And this means that the magnetic ground state of this chain cannot be collinear. It must be a non-collinear ground state. And here you see the model now, which is in agreement with the experimental data. It's basically a spin spiral here with a 4-atom periodicity, meaning that we have about a 90-degree angle from one atomic side to the next. So that means that we have now constructed exactly the type of model system which the theorists proposed and argued that here in these kind of systems you can really have a chance to observe these Majorana states, these zero energy modes right at the ends of the chains. So let us have a look now to the electronic states, spatially and energetically resolved. So, and it's extremely important to be able to look at both ends of a perfect chain, because these Majorana states are predicted always to appear in pairs. That means if we have Majorana states, they have to show up simultaneously at both ends of a perfect chain. And we have to make sure that there is not even a single impurity in this chain, because these impurities might also, of course, induce low energy states. So here you can see now, first of all, again, the spectrum here measured with local tunneling spectroscopy on the bare rhenium substrate here. And here, if you get a little bit closer to the chains, you see you already fill in some state density in the gap, but still you see some pronounced gap. And now we are going to measure, of course, also on the chain and at the chain end as a function of energy. So I'm going to sweep the energy from plus 1 millielectron volt above Fermi level to minus 1 millielectron volt. This is what you are going to see here. Look at this red bar here. So we first are outside the superconducting gap energy. And now look at the spatial distribution of the electronic states once we enter now the in-gap region. We see states here inside the chain, but in particular at zero energy, you see here a very pronounced spectral weight even leaking into the superconductor. And this is a very pronounced feature here right at zero energy. If we go away from zero energy, as you see, then this state right at the end disappears. There was a state here which is actually a von Hove singularity in the one-dimensional Shiba band. And then, of course, we are again outside of the superconducting energy gap. So clearly at zero energy, we observe these very pronounced zero energy modes here, but we can also see that there is some overlap with the finite energy states, the trivial Shiba states. This is a problem which I'm coming back just in a few minutes. But first, let me analyze now this data in more detail. In particular, we can look from the single iron atom up to 40 iron atom chain. So we can really look at the evolution of the states here as a function of chain length. And we have the data for all the different chains. I only have here a subset of data for some particular chain lengths. And the plots I'm going to show now and in the following are very important. So on the y-axis, we have here the energy, and on the x-axis, we have the spatial coordinate along the chains. And so as a function of chain length, we can look, for instance, at zero bias conductance profiles here. And this is shown here, zero bias conductance profiles as a function of chain length. And as you can clearly see, if the chains get longer and longer, we see more and more pronounced state density right at the ends of the chains here. You can quantify this and look at the zero bias conductance here as a function of chain length given by the number of atoms in the chain. And you see that we have a certain conductance here in the center of the chain. But if you look at the ends of the chains here in red, we see that above a critical chain length on the order of 12 iron atoms or so, we have a drastic increase of state density at zero bias here at the ends. And this means that these are clearly additional states showing up. Now, in order to interpret this, of course, we have to get back to our theory colleagues. And the beauty is that we can really make a one-to-one correspondence now between experiment and theory because we have controlled everything. So we can do ab initio electronic structure calculations. These were done by Levente Rocha and co-workers. They have used, of course, exactly the input concerning the geometry, the chemical nature of the system, and also the spin spiral ground state, which we deduced from experiment. And then the results of the ab initio calculations were then used as input for tight binding model calculations to look at topological phase diagrams and the properties of these hybrid systems. That was done by Tore Poske in our theory department of Hamburg University. And the results are shown here. First of all, you can see here in the local density of states plots spatially resolved at zero energy, that if the chain length is rather short, then basically these zero energy modes from both ends overlap drastically. There's a huge hybridization, and you cannot speak of separated states at the ends. And this still holds for about 10 iron atoms. But if you go then towards 20 iron atoms or 30 or 40, you see a very clear separation of these zero energy modes here. So there's only very, very little hybridization still there here if we have 40 iron atoms on rhenium 0001. Of course, this depends a lot on the particular type of hybrid system, as we will see later on. But for iron on rhenium, we achieve already a very good separation of the Majorana end states for 40 iron atoms. And theory, of course, can also tell us if we really have Majorana states present in the system, because theory can now calculate the topological phase diagram where we plot here on the y-axis the chemical potential and on the x-axis the exchange splitting J. And for our parameters, for our system, which are coming from the ab initio calculations, of course, we have the chemical potential and we have the exchange coupling J. And with these parameters, we see that for our system of iron chains on rhenium, we are deeply in the topological non-trivial regime. So meaning that we can really interpret these zero energy modes as Majorana states. But let's come back to this problem of interaction of Majorana states and finite energy Shiba states. And this has also been looked at theoretically. So here again, there's a plot now for 20 iron atom chain on rhenium, where here again we have energy and here the spatial coordinate along the chains here. And this is a calculation taking into account the thermal smearing at a temperature, and this is the measurement temperature indeed in our experiment, namely 350 millikelvin. And one can see indeed that the finite energy Shiba bands, they bend a little bit towards zero energy here, overlapping partially with the zero energy modes. And this is, of course, something one does not want to have. Now, in theory, of course, we can go to lower temperatures immediately. This can be modeled. So this has been done by Tore Boske. So he basically modeled the situation for 35 millikelvin. This is a temperature which we can reach, for instance, with a dilution refrigerant system. And now you can see that the zero energy mode is becoming very nicely separated from the finite energy Shiba bands here. There's a clear gap in between the Majorana modes and the Shiba bands here. And indeed, for this mode, as I said, it was theoretically confirmed that this corresponds to topologically non-trivial states. So that means that experimentally we either have to go to lower temperatures with a dilution refrigerant system, or an alternative would be to go to a superconductor with a larger superconducting gap, so that you can better resolve here the different states, the zero energy modes and the finite energy Shiba states. And this is exactly what we did, because at that time we didn't have here 35 millikelvin available. But let's just replace rhenium now by another elementary superconductor you all know. This is niobium, having the highest TC above 9 Kelvin. Now, the problem with the niobium for a long time was that it was practically impossible to get an atomically clean surface. So in surface science, nobody did studies on clean niobium surface for decades. But actually in our group, Philip Beck achieved this. He could actually prepare atomically clean niobium 110 surfaces, giving us a beautiful possibility to study Majorana physics now for magnetic chains built atom by atom on a niobium 110 substrate. Now here I discuss now results. We have indeed results for all kinds of transition metals, but I'm going to discuss results for linear manganese chains on this niobium 110 substrate. Now the first difference to the iron chains on rhenium is now that we get a multi-orbital structure of the Shiba states. You can see this when looking at the differential tunneling conductance being a measure of the local density of states as a function of energy. And you see here various states inside the gap. Here in gray, you see the background spectrum of the bare niobium. We have a beautiful hard gap, and inside this beautiful large hard gap, we see all the different states here coming from manganese atoms. And when we can sit at the energy of these states and look at the spatial nature of these Shiba states, and you see here the various types of orbital structures of the individual Shiba states here for these manganese atoms, here for negative energies, here for positive energies. These are the partner states of the Shiba states. And another difference is, of course, to the rhenium that we now have a substrate with reduced symmetry. It's only a twofold symmetric substrate lattice now. And this means that we can build chains in different directions here, in 001, for instance, or in 1-1-0. Here, actually, you see now the construction atom by atom here of a chain of manganese atoms in the 1-1-0 direction. It's as perfect as for the iron chains on rhenium. We create chains, again, making sure that each individual manganese atom which we add is indeed a manganese atom. So this is, of course, what we need now to study the physics of these systems. And again, the next step is first to look at the magnetic ground state, to be able to compare the theory one-to-one. And again, we make use of spin-polarized STM to look at magnetic chains here built in various directions with different spacings of the magnetic atoms. So again, there's no other tool available to look at this. Here you see the topography of this chain with a double spacing between manganese atoms here, and we look at the spatial distribution of the spin-polarized tunneling current in different opposite magnetic fields here of minus plus 0.5 Tesla. Then we can calculate the difference normalized to the sum to arrive at the spin asymmetry map. And you see in the spin asymmetry map that you have a periodic change of sign between negative and positive values. This means this is a chain with an antiferromagnetic ground state. On the other hand, if we go to the chain built in the same direction here with a close packed spacing, we obviously have a ferromagnetic ground state, which is characterized by a uniform sign of the spin asymmetry in the spatially resolved map. For a chain in the 1-1 direction, even if we have close packed spacing, we have an antiferromagnetic ground state, and this is different from a chain built in the 1-1 direction, which is this direction, which has then a ferromagnetic ground state. So we can arrive at these conclusions very, very clearly without ambiguity. And as we see, the difference to the iron chains on rhenium is that we have collinear magnetic ground states. These are not spiral states. But in the meantime, theory has shown that even for collinear spin chains, you might be able to observe Majorana physics if you have a sufficient amount of spin-orbit coupling coming from the substrate, from the niobium. So the question is, have we indeed sufficient amount of spin-orbit coupling in order to observe Majorana physics? So here at the end, I show you now the results for two different kinds of manganese chains. A manganese chain of 32 manganese atoms built on niobium 110, first in the 1-1 direction, which is this direction. And it is a close packed spacing with a periodicity of 4.7 angstrom. If we first look now to the differential tunneling conductance as a function of energy, first on the substrate in gray, you see a very nice large gap. That's a hard gap of the niobium substrate, as you have seen before. If we then go to the chain center, and this is shown in blue, we see in-gap states due to the Shiba bands here in the chain center. But look, there is a clear gap also here in this spectrum of the blue curve, where we have no states in the chain center. Only if we go to the chain ends, then we observe here also very low energy states, and especially a zero energy mode here, which is shown here. And if we go to zero energy now in the spatial resolved map, we can indeed see that these states are highly localized at the ends of the chain. We also see, of course, some periodic modulation inside the chain, and this is due to still a hybridization of the Majorana modes from both ends. This is fully in agreement with calculations of a Majorana state wave function, as I will just show in a minute or so. And you clearly see that for the finite energy Shiba states, we have, of course, the major spectral weight inside the chain here. Now, we can go now for plots, as I described before, which are very important to look at, and they clearly show what we have achieved. So here is again the spatial coordinate, and here the energy here for a manganese chain of 40 atoms here on niobium 110. Here you see basically the gap of the niobium substrate. Inside the gap you see basically the Shiba bands here at finite energy, but you also see the zero energy mode here very clearly with very pronounced signature right at the ends. And most beautifully, you see the very large energy separation between the zero energy mode and the finite energy Shiba bands. So that has not been observed before. It's the first time that we could observe this very clear energy separation between the zero energy mode and the finite energy trivial Shiba state. This is extremely important. However, here it's only a 14 atom chain, and we might, of course, consider hybridization effects here of the Majorana states. And indeed, we can see this clearly if we change the length of the chain going from 14 to 15 to 16 atoms, we see that for a 14 and 16 atom chain, we have here beautiful the zero energy mode here, really sitting at zero energy. But for the manganese 15 chain, this state actually splits here. And the splitting, the amount of the splitting is basically due to the hybridization of the Majorana state wave function from both ends. So this is shown here. This is a theoretical calculation of the Majorana state wave function. We basically have here a very special situation where half of the Fermi wavelength is basically equivalent to 2 times the atomic spacing of the manganese atoms. And this is why we get a periodic constructive and destructive interference, so to say, of the Majorana state wave function, and this is exactly the explanation. But still, even the split Majorana state here is still then separated in energy from the other trivial Shiba bands. This is extremely important. And you can understand this, of course, also by comparing the theory. So here there are diagrams of the energy of the states we observe for different chain lengths, for even and odd number of chains. And we can compare this with theoretical calculations, clearly showing that we are here in a regime where strong hybridization is present despite the very good localization of the Majorana modes. So what we have observed here are hybridized Majorana modes in atomic spin chains. Actually, you have to get to chain lengths beyond 20 atoms, beyond 70 atoms in this case, to observe something similar as for the iron chains on uranium. Now, in the end, and this is the last data set I show you, we go now for manganese chains built in the 001 direction on niobium 110. And here you see, besides the topography, the spatial resolved maps of the tunneling conductance. And you see again at finite energies here, basically the signatures of the Shiba bands here inside the chain. But right at zero energy, you see here something completely new and different. There are side features showing up here with a certain periodicity. They have spectral weight basically outside of the chain. And this is, of course, a very, very strange observation. But we confirmed that we have that also for many other kind of chains. This is a longer chain here of 51 manganese atoms. And again, you see these side features. There are more maxima here along the chain, but still same signature as shown here. And even if we replace manganese by iron for iron 16 chain, you can also see these side features here at zero energy. And this is explained recently by a very nice work by our theory collaborators, Stefan Rachel in Melbourne and Dirk Moore in Chicago. They have shown that indeed Majorana states can show up as side features if we have multi-orbital states of the magnetic impurities. So these are calculations now for exactly a manganese 34 atom chain, which resembles closely what we observe experimentally, and also for the manganese 51 chain, you can see the beautiful agreement here between experiment and theory. So what was done to arrive at this result was that we did very sophisticated ab initio calculations for manganese chains on niobium. That was done by Harald Jeschke. It's a huge task to calculate this because you end up, of course, with hundreds of bands. It's not just a one band model which applies here, of course. You have to look at all the bands. But of course, for Majorana physics, only the low energy bands are decisive. But still, even if you focus only on the low energy bands, you end up, of course, with a lot of bands you have to take into account. And that was done by Stefan Rachel and his co-workers to take into account all these low energy bands, and then using this as an input for tight binding model calculations to derive the phase diagrams, again as a function of chemical potential and as a function of exchange coupling J, and they could then distinguish between the topological trivial and non-trivial regimes. And they showed that for this particular system of manganese chains on niobium 110, built in the 001 direction, you end up exactly with these kind of spatial distributions. And they confirmed that these are states of non-trivial nature. So And this is, of course, a very important result. And they even could explain these double eye features observed earlier by the Princeton group, but with a completely different type of theoretical explanation. This is quite remarkable also when considering earlier results, also of a completely different system, namely iron chains on lead. So in the end, that's the last point I would like to make. It's not only a
Roland, 3 minutes.
these Majorana states, I'm just coming to an end, but to do manipulations, to do braiding as, of course, proposed theoretically. So you can make a sequence of operations of these Majorana states, exchange them, and look at the non-abelian quantum exchange statistics. And this is something we have started to look at. We can build also these tri-junctions atom by atom. We can build up more complex network structures, and we can make sure that the chains are long enough to get rid of the hybridization here of both ends here to a large extent. And moreover, as has been theoretically predicted, we can even build circular rings of atoms. And this is also a very nice platform to observe Majorana physics. When applying an in-plane field, you can also manipulate these Majorana modes as theoretically proposed by the Princeton group 5 years back in time. And we are able, with single atom manipulation, also to construct such ring structures, so-called quantum necklaces here of magnetic atoms on non-superconducting and superconducting substrates. So this is an outlook for the future. So to conclude my talk, I have presented the successful bottom-up fabrication of defect-free magnetic single atom chains on clean elemental superconductors like rhenium, niobium, tantalum. I haven't time to focus on tantalum, but there are some first results in literature, as you can see. We have clearly observed the characteristic signatures of Majorana states by spatially energy and spin resolved scanning tunneling spectroscopy. We have observed zero energy modes, which are clearly separated in energy from trivial finite energy Shiba states within a hard gap of the niobium substrate. And for the very first time, we have analyzed multi-orbit systems and their spatial distribution, especially of the Majorana states, which show side features which have been explained theoretically for these kind of chains. And so we know that the spatial signatures now of Majorana states can be of different nature. So in the end, I would like to acknowledge my collaborators, Hovan Kim, who did the pioneering work on the iron chains on rhenium, Lukas Schneider, Philip Beck, Jens Wiebe, who did the fantastic work on the manganese chains on niobium, Levente Rocha doing the ab initio calculations, Tore Poske doing tight binding model calculations, and our theory collaborators here, Dirk Moore in Chicago, Stefan Rachel in Melbourne, and many others. I would like to thank the funding agency, the European Research Council in particular, for supporting our project on the atomic scale design of Majorana states and the innovative real space exploration. And I would like to thank you very much for your kind attention.
Roland, thanks much for your beautiful talk and really enlightening. Now, since, because of unfortunate delay and we have too much other session, we probably have time for one good question from the audience. Go ahead.
Fantastic work and fantastic talk. Thank you. So the question is about what you discussed at the end, the application of external magnetic field. So how is it then going with spin-polarized STM? Is it somehow detrimental for spin-polarized STM, or you can use it?
That's the question. Spin-polarized STM was also very hard to use for several tests. And look at the literature in the world, for many studies to do, and this, where they are making use basically for instance, based on very large spin state of one atom. And the Roland test is around the spark, and based around the spark, because energy scale is here, the signal energy is much lower for this trend, and we change coupling of states with environment.
Thank you very much. One more brief question. Well, if no, let's thank the speaker for absolutely brilliant talk. And with this, we close the session.